Well, in the last few lectures, we looked into the object modeling and the different features of object modeling. Mainly, we have discussed about the different abstraction mechanism, that is how to define the relationships among the objects. We have considered the abstraction mechanisms such as generalization and specialization, aggregation and grouping, and how they help in defining complex object structures. We have also talked about the different features like polymorphism, object communication, and how the the same method can be overloaded in the subclasses of a class. Now, these features that we have so far concentrated helped us in defining the static behavior of the objects, in the sense that the structure of the object is fixed at the beginning, or the schema of the object class is given, together with the methods that the objects can will perform in when a certain messages are received are also defined at the beginning. However, in many real life applications, one need to look into the dynamic features of the objects, mainly because how the objects act in response to certain events or something that is happening outside the world. For instance, when we are working with a machine in a computer, when a mouse is pressed. Now, as a consequence of the mouse pressing of the mouse button, some actions have to be taken. Similarly, when we are also modeling, or we are trying to develop an inventory management system, and we know that in an inventory management system, when the stock of a inventory system, when a stock of a particular item, say an item stock, falls below the amount the item stock falls below a particular level, which is sometimes called the reorder level, then it is necessary to place new order for that stock. Now, this is such an order, however, will not be placed until the stock amount of the stock of the item is well above the reorder level. So therefore, when the stock falls below a special level, no further probably the same amount cannot be issued to the different branches of the company which is asking for that stock. Now, this kind of, but when that such an amount, this amount of stock will fall below the reorder level is not known a priori. It will depend how many requests are coming to the inventory system for issuing of that item. So this kind of situations which says that the behavior or the function operations that object will have to perform will depend on occurrence of some phenomena or some events in the external world, requires that we also focus on the problem of the dynamic aspects of the objects. And there are different ways of modeling dynamic behavior of the objects, among which we will now briefly discuss in this lecture the cases of when it is described by some of these items called events and states. Now, these are in this model we will see that events are something which may occur outside the definition of the objects and the object will perform some operations depending upon when the event has occurred. So therefore, to define what is an event, we can say event is something which occurs at some time instant. Now, example of such thing will be that, for instance, when we press the left button of a mouse in a computer, now this pressing of a button of a mouse by a user occurs at some instant but may not be at a definite time instant which can be said a priori. Similarly, when a train arrives in a platform or a flight, say Indian Airlines flight to Bombay from Calcutta departs. So now the departure of a flight or the arrival of a train is an event which takes place at certain time intervals. So we will say that this is what is meant by an event, that something which occurs at definite some time intervals, time instance. Other examples will be the receipt of an order, the student or the patient arriving in a hospital for treatment. Now the arrival is an event which again has or which occurs at some time instant. Now as a consequence of this, moreover, the another thing we have to do note that events may be concurrent, meaning that more than one event may occur at the same time instant. For example, it may be the case that in if you have the multiple platforms in a train in a station, more than one train can arrive in the platform, different platforms, or from one platform train departs, whereas from another platform a new train arrives. So these two, arrival and the departure of trains in a platform will be concurrent. Similarly, when we are placing orders to different vendors, or we are receiving the system, you have an order processing system. When the orders may be received from different customers at the same instant of time. Again, the order may be for different items or maybe for the same item. So therefore, while considering the events, one has to look into the cases. The events may be very simple, like arrival of a train, or departure of a flight, or receipt of an order, whereas they may be concurrent, or it may be that some event required that events may be composite, complex in nature, in the sense that the event to which an object or the object will respond will depend on not one event but occurrence of multiple events at a certain at different time instance. Say for instance, if we can say that if the train arrives in say platform number 1 and another train arrives in platform number 2, then it will be at the same time instant. Then the passengers can board the new train which arrives in platform number 2 from platform number 1, from the one which has arrived in platform number 1. So therefore, the occurrence that both the trains have arrived at the same time instant, or it may be the case that one has arrived after the other, slightly after within a very short time interval after the other. It may be possible to exchange the passengers from one train to the other. Similarly, we may have a case in which, say for example, in a case of a bank, in a bank, say there may be two requests. The user is making a request, say debit. User 1 makes a request debit from his or her account, and then another user 2 also asks that the credit, that certain amount to be credited in the account of user 1. Then it may be the case the bank may have a policy that the amount that user 1 will be allowed to have an overdraft provided another user credits the amount, credits this the balance amount within the same day or within an hour, or if such an event occurs, then certain actions will be taken. Now, so therefore what we are talking here is that events can be simple. Maybe simple means single event. They may be concurrent. we may have to deal with the event compositions, where the compositions of the events means that it can be, the composition operators means that if the event 1 and event 2 has occurred, it can be or, that means both the either of the events has occurred, then it performs some action, or the or it may be in sequence. That is, if the event 1 has occurred followed by event 2, then we will be interested in that. The examples of OR events would be that suppose there are cars coming to the intersection, and it is found that either the traffic light that is that is no police, that is no red light, or even if there is a red light, there is no car on the other side or the other side of the road, the cars may be allowed to cross. That is, cars will halt and then proceed. If so, there may be either of these cases. So this will be an event condition that there is no car waiting on the other side on other roads. That is, in an intersection you have. So in this side there is no car waiting, and if a car arrives here and finds that there is no car waiting on the other side, and even if the light is red, then after stopping here, after stopping, it may proceed to cross the intersection. So this is a case either of or of the condition or the or condition. Similarly, one can have, say, event 1 followed by event 2. If this happens, that is, event 2 occurs in a sequence, then one will be some actions will be taken by the object under considerations. For example, in case of in a chemical plant, if it is found that if the temperature has become high and a later instant of time, slightly later instant of time, the pressure also is high, then you raise alarm, or that means there exists a certain problem in the plant. So the both pressure and the temperature and the pressure becomes high within a certain period of time, then there is a problem. So these are this is what we mean by events. And events, well, as we know in real life example, there are different kinds of events, and when we are trying to model an information system, one has to identify what are the events of interest for a particular class of objects, and whether the event that it will be of interest will be simple events, whether they will be concurrent events, or the events can be there we will be looking at the event compositions. The next concept that we have discussed is the concept of the state. Now, the state is essentially an idea in which we try to divide. We specify the object in such a manner that we can somewhat partition the behavior of the objects depending upon the so-called the state levels, and such that the objects will perform different operations perform different operations in different states. And secondly, the action that it will perform in response to an event will depend on the state which it is currently in. So therefore, if we follow that type of philosophy, then we can define a state of an object to be sort of an abstraction of the attribute values of its attribute values and the links of an object. That means, that the object is completely specified by once the structure of the object is known, the values, its attribute values, and also the other objects to which it is referencing through links, the different types of interrelationships it has with other objects. So, at a typical example of an object having different state, for example, an order. If you think that an order is an object, we may think of the order may be partially filled or fully executed. That means when you have completely delivered or delivered the item that has been ordered to you, then you say that it is a fully executed, otherwise it will be partially executed. Other examples is that suppose a student data student object. Now the student object may be in a different state depending upon whether the student is waiting for registration to a course, whether the student has already registered, whether the student is waiting for the grades, and so on. Other examples, suppose we are looking at a library database in which we have a book as an object. We can define the state of the book in the different in like this, that we can say that the book has been issued to an user, book is available in the library, that means it is not used to the user. The book is not available to the in the library, neither it has been issued to the user, but it has an order for that book has been placed to a supplier, although the book has not yet been received. Similarly, we can have the book which has already been received but not yet been made available because you have not entered into the stock. Lastly, a book can be maybe lost. So now, so we can say we can look at the book in the different states, and depending upon the state in which it is in, it will respond to the events when it occurs in the external world. Like for example, when if the book is in ordered state, when the supplier supplies the book, it will change. You know that the order the book is now received. It will go into the state in which is the call that has been received, and the next it will be and it will be appropriate accession number will be assigned to it, and then it will go to a state it's available in the library. So therefore, we can define the behavior or the operations that can be performed on a book object depending upon its current state and how does it react to the events. So next is the concept that the thing we have been talking is that how these events, so therefore the events and the states will be clearly will be interlinked with each other or will be interrelated to each other to describe the dynamic behavior of the object. That is, the events identity is a sort of, we can think it of defining an occurrence with respect to time, and our state is defining how the object is what is currently in, what is the behavior, what are the things object can currently perform, and then when an event occurs, the object should change its state. So this is what we call the state diagrams. It specifies, it is a state of, so this is described by a state diagram which relates states and events. The state diagram will specify the state sequence caused by an event sequence. That means if you have a sequence of events are occurring, what are the states, how it will change the states from one, that means how it will go from one state to the other. And one can, as we'll see slowly, one can define, say, a state diagram as a graph with the nodes at the state and with the directed arcs which are called transitions, and it will be labeled by the event names, meaning that whenever that event occurs, it will undergo such transition and to describe the dynamic, and that will describe the dynamics of an object. To see about a state diagram, let us take a simple example. We have an order object. Now initially order, as you create a new order, so this becomes a new order, and the order when it is created, it will be in a state which we call the partially filled. Now this partially filled, this is the state name of a state, and another state name is fully filled. And when the object is in this state, now suppose a delivery is received such that the amount ordered is greater than the amount received. In that case, we know that there will be some balance amount left, and the object, all the amount that has been ordered has not been received. So therefore, the balance amount is 0, and we can say that the order as an object or it remains in a partially filled state. And in the partially filled state, then it will again, it can also receive, can receive another order, another delivery from another supplier. And as a consequence of that, so that when the amount received becomes equal to the balance amount, we can say that order has been fully filled or fully executed. So therefore, this is a case of a state transition diagram. As a consequence of this event, delivery even received is an event. It returns to, it undergoes a state change. Now, along with it, we normally, what we will do, with each such state transition, we'll also associate, that is, with each event, we'll associate a certain condition that has to be specified, that will be specified, which will identify what will, under what conditions such a transition will take place. That, in other words, occurrence of an event automatically in such a situation will not imply the state transition, but the state transition will take place. Such a state transition will take place provided this condition, such a this type of conditions are met. Example here: if the order is in a partially filled state and the event delivery, this is an event. This event has occurred, that the delivery has been received from some supplier, and the amount received is equal to the balance amount. So both these things must be true, must occur, that is, event must have occurred and this thing must have occurred, then it will go to the new state. So this is what we mean by the event and the condition associated. We'll come back to this again. So for example, therefore, we can state diagram, therefore, what does it say? It defines a state transition between one state to the other as a consequence of some events and when certain conditions are met. Further examples would be that, so therefore what we define, state transition occurs as a consequence of an event provided appropriate conditions are satisfied. In the previous example, the conditions are satisfied are, that is, the amount received is less than the amount of order, then it will come to this state, this transition will take place. If the amount received is equal to the balance amount, it will go to the fully filled state. Other examples are, suppose we have a furnace or auto thermostat in which the furnace will be made on. Suppose the furnace is currently in a off state. This is furnace off. This is an off state. Furnace will go to the on state on when this is the transition will specify if the power switch is on set. This is an event. This event occurs, and the condition is that if since the thermostat, the temperature, current temperature that is measured, which they say we have a thermocouple inside it or any other temperature sensing devices inside it, is less than the desired temperature. So suppose you have satisfied that the desired temperature is say 200 degree, and your current temperature inside the furnace is equal to 100. Then when the power switch is on, it will, furnace when it was initially off will be turned on. So this is an example of another example of a state transition. The partially filled order we have just now seen. Other examples can be taken from say the library. It may be, say, book. So book is, this is the book case, and we have seen that the book can be in a different state. Say it is issued to a user. So this is, suppose it is in a state called issued, and then it can go to the state available provided an event user returns. Now when the user returns event take place, then the book, the state of the book is will be changed from issued to available. Similarly, for other types of state transitions in the book case, we can also identify that, like say when the book is, say let us take the case that book is ordered, is in a current state called ordered, and then delivery received, you go to the you have the order has ordered but and has been received but not yet made available. Now in this state, enter stock, we can identify this, that is when it is received, the user must perform that that is the library and must enter the book into the stock, and after doing this it can say assign accession number. So once the accession number, the librarian assigns an accession number, the book I will assume to be it has been entered in the stock and it will be made available. So this is again a case of state transition where the behavior of the book, that the book can be, what are the book object will have different states. Now one thing we may see, that why do I want to partition the books into different states? The reason might be that the amount, the operations that you can perform on a book will depend on the state in which it is currently in. For example, when the book is issued, then you cannot, the book cannot be further issued to anybody. So the operation issue cannot be done when the book is already issued. Similarly, when the book is in a stock, when it is enter stock, the operations might be that you enter into the stock register of the into the book and then put into the catalog, and after that they assign and then when this assign accession number is done, it's made available. So and in this state you cannot make the book cannot be issued to any user. So therefore what we are seeing here, that the state of an object, as we'll see, will identify what are the operations the object can be performed. We can slow that not all operations can be performed in every state, it may not be feasible. So unlike in the original static modeling, when if you recall that in a static modeling, when we define the operations or the methods to be performed on a book, on an object, it is not, it is always all those operations will be always available in that for all instances of the objects in this class. Whereas here we are saying that the operations that can be performed on an object will depend on the state in which the object is currently in. The next thing that we'll have to see, that we have already defined what we mean by the state transition diagram, what the state transition and the state transition diagrams are. The next thing we'll note that it is not always very interesting that we only partition the objects into different states and define the transition. In addition, it may be necessary or it is desirable that when in order to define the dynamic behavior of objects, that we should also associate certain actions whenever such transition takes place. Like, so actions, or what we will mean by the operations, we will say that in response to events, when objects perform some operation, that means whenever such a state transition is taking place, then after that, as a consequence, objects move from one state to the other. As a consequence of this, when such transition takes place, we may say that some operations had to be performed. So what we are having, we are saying that the model that we are describing will involve event, the three components here: event, condition, and action. Now the action part, these three together will define the dynamic behavior of the object. Now the actions might be, as we are just now mentioning, That typical example might be that when an item order is received, the operations might be that perform and enter the item received into the stock register. Similarly, when a patient arrives in a hospital, you assign the operations might be the patient is assigned to a doctor, or the operations might be that the patient is admitted to a ward. Again, if a temperature is high and alarm rings, say for example this is the condition, the temperature is high, is satisfied, and there exists an alarm bell is ringing, this is an event, then open the coolant flow valve. So this is another action that has to be performed. So what we have now, we have come across, we have described so far that the dynamic behavior of the object will be determined by the event that object subscribes for, the condition under which such an appropriate event, the transition will take place, and the action that can be that it will perform as a consequence of the event. Now, when we describe the class, therefore class specification, we must therefore clearly identify the states of the objects which in this class. We'll also should identify the events which the objects in this class will subscribe for, and the operations that can be performed as a consequence of the events. So along with the static structure of the objects that we have defined in terms of the abstraction operators earlier, the dynamic abstraction mechanisms, the dynamic behavior will be described using these three features, and that will give us the complete specification, dynamic behavior of the object. Now the next question comes that we have described that when we define a class, we can define a class, say B, say we have a class A which is a dynamic object and B. We may allow specializations of that. In this case, we have seen how the object of the class B will inherit all the attributes and the structure of the objects of the class A. But in this case, it should also inherit the state and the state transition specifications that may take place for the objects in A. So therefore, the inheritance that we have so far earlier described has to be generalized to deal with the inheritance of the dynamic behavior. Now, there may be some problems in this situation, that when the class B tries to modify the behavior or tries to add few new states in its while describing its behavior, and so in such situations it might be desirable that that some restrictions or sometimes some constraints have to be followed while defining the behavior of these inherited classes. A typical approach that is often suggested is that when we look at the composite object, say we are defining a state transition. For example, in class A we have a state S1, from here it goes to state S2, and with respect to an event A1 and certain conditions C1 to be satisfied. So this is in class A. Now when in class B we try to inherit, we may think it of that we'll treat the class B as an extension of class A. Now we can think it of this state itself as a composite state, and we can think it of like this, that this corresponds to a state S11 and then S12 and say S13. So we have say E11, E12 and E1. So what happens here, this is what we sometimes call the the upper level state, the states itself will be nested. So the nesting of states often helps in describing that is the lower level objects, that is the class B objects, which are essentially inheriting the behaviors of class A, and in which class A looks at the states of of class B in a more coarse level, and so therefore one can think it of the states in class A itself as a state transition system, state transition diagram, in which the state S1 is refined into further level, into smaller number of states, and these state transition takes place when the object is, when we are looking at more specialized version of the objects of class A. So this kind of nesting of states often is followed in describing the generalization and the specialization relationships. Similarly, in other, we may also define the event hierarchy, and to describe that whereas the upper level classes, that is the parent class may be interested in looking at the more that the course level events, or the events which is at the higher level of the hierarchy, to define the transitions, whereas the objects at the lower level, that is the subclass level, will look at the events with a much refined level, the much finer level, that is lower level of the events in the hierarchical structure. Now these will be described in detail later on when we look at the object modeling in further detail, and it will be done by my colleague Dr. Sarkar. So what we have seen today in this lecture is that it is possible to capture the dynamic behavior of the objects, and while capturing the dynamic behavior of the objects, it may be one can take help of the concept of events, concept of states, and the state transition diagram. And with the help of state events, states and action, we can as a consequence of the state transition, the objects will be allowed to perform certain operations, and that these together will describe the complete dynamic behavior of the objects. We can extend the concepts of generalization of specializations of such complex objects, so that lower level objects, that is the objects at the lower level in the class hierarchy, will look at the states in a more finer detail, that means in the more refined level, at the more refined level than at the upper levels. One can also define the hierarchy of events. So this concludes our lectures on object modeling, and what are the basic concepts of the object modeling are involved, and how they can be used in capturing the behavior of the different information systems. And the next class, what we will now look at is the language aspect. That is it is very easy. So we have so far described in a broadly what are the different features that an object oriented system should have. Now while implementing such a system, we will need certain programming languages, and we'll take help of certain programming languages, and what we'll examine that there are different object oriented programming languages have been introduced, and what we'll do is that look at the features of such programming languages and go a little bit in detail with one language at least.